Async and await makes writing .asynchronous code really easy. Just imagine the callback nightmare we'd be in if it didn't exist. But here's what's crazy. The .compiler completely rewrites your async functions into something totally different, a state machine. Let's see what's really happening under the hood. Before we see the transformation, let's quickly understand what a state machine is. A state machine is just a program that can be in different states and moves between them based on events. Think of a traffic light. State 1 could be red, and after some time passes, it turns to state 2, which is green. After some time, state 2 could be green, and once some time passes, it goes to yellow, and of course then to red. The traffic light remembers which state it's in and knows what to do next. Your async functions work the same way. They remember where they paused and know how to continue. Now, here's the big secret. Async await is just syntactic sugar. The .compiler completely transforms your async functions. Let me show you what happens to this code. The compiler transforms it into this state machine. This is a bit simplified, but I hope you get the gist. Notice what happened here. Each await becomes a different state. Your function becomes a state machine, and local variables are preserved between states. With multiple awaits, you get multiple states. Each state can access variables from previous states because they're stored in the state machine. This is why this works. The variable A is available when we get to the second await because it's stored in the whole state machine. Here's something important about how these state machines actually get scheduled. Dot runs on a single thread with an event loop, which is basically just a loop that continuously checks for work to do and executes it. The event loop manages two separate queues, Microtasks and Events. This two-queue system exists because some asynchronous work is more urgent than the others. Microtasks are for high-priority internal operations like async function continuations, while events handle external things like user clicks, timers, and file I/O. When your state machine resumes after an await, it gets scheduled as a microtask, which has higher priority than regular events. The event loop always processes all microtasks first before moving on to any events. You can see this priority system in action in this snippet. Notice how all the microtasks run before the events, even though they were scheduled in a mixed order. This is why async await feels so responsive. Your async function continuations get priority over other things like timers, I/O events, and user interactions. When you await something, your continuation gets added to the microtask queue, which means it runs it as soon as possible. This makes async await much more predictable than manually scheduling it with future constructors. Async await hides this complex state machine transformation behind simple syntax. When you write await, you're creating a function that can pause, let other code run through the event loop, and then resume exactly where it left off using the microtask queue. That's how Dart gives you the readability of synchronous code with the performance of asynchronous execution, all while maintaining proper scheduling priorities. I hope this helped you understand async await a bit better in Flutter. Thanks for watching, and I'll see you next time.